Something about the way 3I Atlas spins does not sit comfortably within expectation. Interstellar objects are supposed to tumble chaotically after millions or billions of years wandering between stars. Their surfaces fracture, their volatiles erupt unevenly, their rotational states evolve unpredictably. Yet this object rotates with a steady rhythm of just over 7 hours. Its jet does not spray randomly into space, it wobbles with precision. It precesses around a stable axis, and that axis is aligned within a narrow angle of the Sun object direction. A 7-hour rotation alone would not be extraordinary, but a 7-hour rotation paired with a coherent, tightly collimated jet that sweeps in a predictable cycle, and an axis that appears statistically unlikely in its orientation forces a harder question. What exactly are we looking at? Is this merely an unusually well-behaved cometary nucleus, or is it an object whose physical state challenges assumptions about how interstellar debris behaves? The measurements themselves are not speculative, they are precise. After its closest approach to the Sun on October 29, 2025, the rotation period of 3I Atlas was determined using two independent techniques. The first method tracked the orientation of a prominent anti-sunward jet observed in filtered images from the Hubble Space Telescope. Between November 20th and December 27, 2025, the jet's projected position angle on the sky oscillated by approximately plus or minus 20 degrees. That oscillation repeated every 7.20 plus or minus 0.05 hours. The motion was not erratic, it traced a consistent precession around a stable rotation axis. The second method examined brightness variations. Between December 9th and December 22nd, 2025, photometric observations revealed periodic fluctuations in total flux of roughly plus or minus 30%. The derived period from brightness modulation was 7.136 plus or minus 0.001 hours. The two values differ slightly, but the discrepancy is small and attributable to systematic effects. Combined, the data support a post-perihelion rotation period of approximately 7.1 hours. Crucially, the brightness variations do not originate from reflected sunlight off the nucleus. Earlier imaging showed that less than 1% of the scattered light comes from the solid surface itself. The dominant contribution arises from dust and gas in the surrounding coma. As the nucleus rotates, the active jet sweeps around the rotation axis. That sweeping motion modulates the dust column density along the line of sight, redistributes material within the photometric aperture, and changes the effective scattering phase function of the dust grains. The periodic brightness signal is therefore jet-driven, not shape-driven. Prior to perihelion, measurements of jet precession indicated a period of 7.74 plus minus 0.35 hours, consistent within uncertainties with the post-perihelion value. However, brightness variations before perihelion suggested a longer period of roughly 16 to 17 hours. The difference likely reflects a change in the number or geometry of active regions following perihelion. If only one pole was illuminated before perihelion, but both poles became active afterward, the effective modulation frequency of the coma could have doubled without altering the underlying spin state. The jet's average position angle after perihelion was measured at approximately 270 degrees, plus minus 3 degrees. The Sun 3I Atlas axis during that time was about 290 degrees. This implies that the rotation axis is aligned within roughly 10 to 20 degrees of the Sun object direction. In interstellar space, such alignment has a probability estimated between 1.5 and 6% if orientations are random. The axis itself would have been set long before entering the solar system. Its near alignment with the Sun is therefore statistically unusual, though not impossible. That is the measured rotational picture: a stable 7-hour spin, a precessing jet, brightness modulation driven by dust outflow, and an axis oriented in an uncommon direction. But rotation is only one part of the puzzle. Since its discovery, 3I Atlas has been described as peculiar, with its unusual properties grouped into a series of anomalies by Avi Loeb. Among the main anomalies he highlights is the object's orbital geometry. Its trajectory moves opposite the direction of planetary motion and is aligned to within 5 degrees of the ecliptic plane, the flat disk in which the planets orbit the Sun. The quoted likelihood of such precise alignment occurring at random is approximately 0.2%. Loeb has suggested that this degree of fine-tuning raises the possibility that the object was not drawn randomly from an isotropic reservoir of interstellar debris. Another feature concerns its arrival direction. 3I Atlas entered the solar system from a region of sky that lies within 9 degrees of the location associated with the historical WOW signal, the narrowband radio signal detected in 1977 that has never been conclusively explained. The estimated probability of this directional coincidence is roughly 0.6%. While coincidence alone does not imply causation, the proximity has been cited as statistically noteworthy. The object's activity pattern has also drawn attention. Both before and after perihelion, 3I Atlas displayed a sunward jet, sometimes described as an antitail, that does not appear to be a mere projection effect caused by viewing geometry, unlike familiar cometary antitails. Instead, the feature is interpreted as a physically real jet directed toward the Sun. Loeb has proposed that sustained sunward jets could represent a technological signature rather than purely sublimation-driven outgassing. Timing is another anomaly category. The object's trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter, while remaining unobservable from Earth at perihelion due to solar glare. The combined likelihood of this configuration has been estimated at approximately 0.005%. Of particular interest is its forecasted closest approach to Jupiter on March 16, 2026. The predicted peri-Jove distance is 53.6 million kilometers, nearly identical to Jupiter's Hill radius of 53.5 million kilometers, the boundary within which Jupiter's gravity dominates over the Sun's. This near match has been interpreted as potentially significant, raising the speculative possibility that the object could release devices into stable Jovian orbits, including Lagrange points where minimal orbital corrections would be required. Mass and velocity further distinguish 3I Atlas from previous interstellar visitors such as 1I Oumuamua and 2I Borisov. Its nucleus is described as several orders of magnitude more massive than either of those objects, while also moving faster. Loeb has argued that there may not be enough rocky material in interstellar space to deliver bodies of this mass into the inner solar system at a rate of roughly once per decade purely by chance. This has led to the suggestion that 3I Atlas could have been targeted toward the inner solar system rather than arriving randomly. Its chemical composition presents another reported anomaly. Analyses of the gas plume indicate a higher abundance of nickel relative to iron than is typical for known comets, along with a nickel to cyanide ratio orders of magnitude larger than cometary norms, with likelihood estimates below 1%. Because industrially produced nickel alloys on Earth often exhibit elevated nickel fractions, Loeb has proposed that such ratios might reflect artificial surface material, though natural explanations have not been ruled out. The dynamics of its jets also raise questions. The object exhibits tightly collimated jets in both the sunward and anti-sunward directions, maintaining orientation over distances approaching 1 million kilometers. It has been argued that producing the required mass flux through ordinary sublimation would demand an unusually large effective absorbing surface area. This has prompted the suggestion that the jets could originate from technological thrusters rather than purely volatile-driven processes. Finally, near perihelion, 3I Atlas exhibited measurable non-gravitational acceleration. While cometary outgassing commonly produces such effects, the magnitude and context of the acceleration have been cited as consistent with the possibility of engine-like thrust. In Loeb's categorization, this joins the broader pattern of orbital, compositional, and dynamical anomalies. All of these features converge toward a key date, March 16, 2026. On that day, 3I Atlas passes Jupiter at a distance comparable to the boundary of Jupiter's gravitational dominance. Whether this encounter results in gravitational deflection, additional jet activity, fragmentation, or no visible change at all will be closely monitored. If the object were to release smaller bodies into Jovian orbit, detection would depend on timing, geometry, and instrument sensitivity. If nothing unusual occurs, many of the more dramatic interpretations will weaken. The coming months, therefore, represent an observational test. Rotation has already revealed a stable internal clock. The jets have demonstrated coherent structure. The axis alignment has proven statistically uncommon. The trajectory and composition claims remain under scrutiny. Jupiter now becomes the next checkpoint. The 7-hour spin is real. The wobbling jet is real. The unusual alignments are measurable. What they ultimately signify is the question that remains.